Hello everyone, and thanks for joining us on today's webinar on how to design a robust wireless biotelemetry system. My name is Amin. I'm an Alpha Application Engineer at HFWorks. So before we start, I would like to give you a brief summary about what we are going to discuss today. So first, we'll talk briefly about biotelemetry. After that, we'll look at some of the antenna design challenges. Following that, we'll have a case study of implementable antenna, along with some simulation results. At the end, we'll have a live demo, so in case if you have any questions, I'd be happy to answer them at the end of the presentation. So before we begin, I would like to give you a brief overview about HFWorks. HFWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a very wide range of applications, ranging from electric motors, generators, transformers, and power electronics, to antennas and various wireless circuits and components. HFWorks is an antenna and electromagnetic simulation software for RF, microwave, millimeter wave, and high-speed digital circuits. It uses state-of-the-art finite element solvers and machine technologies to compute fields as well as antennas and circuit parameters. It also comes with an integrated electrothermal solver. So if you want to learn more about our products, you can always visit our website at www.emworks.com. Alright, so let's talk about biotelemetry. What do we mean by biotelemetry? Biotelemetry is simply a technology that involves the wireless transmission of biological signals and data from inside the body to an external receiver or monitoring system. Implantable antennas are an essential component of wireless biotelemetry systems, as they enable the wireless transmission of data from inside the body to an external receiver. Some applications of biotelemetry include medical implants. Implantable antennas are commonly used in medical implants such as pacemakers, defibrillators, and neurostimulators. These devices use implantable antennas to wirelessly transmit data from inside the body to an external receiver or monitoring system, allowing healthcare professionals to monitor the patient's condition and adjust the device settings remotely. Moreover, the antenna can also be used for remote patient monitoring. For example, they can be used to monitor glucose level in diabetic patients or to monitor blood pressure and heart rate in patients with cardiovascular disease. These allow healthcare providers to monitor patients' vital signs remotely, reducing the need for hospital visits and improving the patient outcomes. Sport medicine has also seen a revolution with biotelemetry-enabled wearable devices. Athletes can have their heart rate, respiration, and other critical parameters monitored, enable trainers and coaches to make data-driven decisions and prevent injuries. Finally, biotelemetry is essential in research. For instance, it can be used to study the effect of drugs on the bodies or to monitor the progression of diseases. Implantable antennas can provide researchers with real-time data on biological processes, allowing them to better understand how the body works and develop new treatment for diseases. Alright, now let's look at the challenges associated with designing implantable antennas. One of the most significant challenges in designing implantable antennas is miniaturization. Implantable antennas must be small enough to fit within the confines of medical devices while still maintaining optimum performance. Achieving this balance is a significant challenge for designers. Another critical challenge is ensuring biocompatibility. The antenna must not cause an adverse reaction or interfere with the body's natural functions. Thus, materials used in the antenna must be biocompatible with the human body. Patient safety is also a crucial concern in designing implantable antennas. The antenna must operate safely and effectively within the human body without posing any risk to the patient's health. Finally, signal attenuation is another challenge in designing implantable antennas. The antenna must be capable of transmitting and receiving signals with minimum attenuation, even in the presence of various tissues, fluids, and other materials in the human body. Alright, so let's look at a case study of implantable antenna. The proposed antenna has rectangular spiral shape and is printed on high permittivity substrate. High permittivity substrates help to reduce the size of the antenna. The antenna is covered with the biocompatible superstrate, and this helps to prevent short circuit between the metallic radiator and the conducting body tissues. The antenna is designed to operate in MACS band, which is the most widely used frequency band for medical implants applications. The antenna has size of 20 mm by 10 mm by 1.65 mm. The antenna is electrically small. The length and the width of the antenna are much smaller than the wavelength. The antenna is placed in a simplified human tissue model. The tissue consists of 3 layers, namely skin, fat, and muscle. Return loss is one of the important parameters when designing antennas. So as we can see from the graph on the right, the antenna resonates almost at 402 with return loss of almost minus 25 dB. The frequency band of the antenna is from 397 MHz to 405 MHz, and this lies in the MACS band. On the left, we can see an electric field animation along with the meshed geometry. SIR is another important parameter to consider when designing antennas. Looking at the SIR distribution on the right, we can see that the maximum SIR value is 0.07, which is below the recommended level of 1.6 watt per kilogram. I just want to mention that this SIR distribution is for an input power of 5 milliwatt. On the left, you can see a 3D radiation pattern of the antenna. The antenna has a maximum gain of minus 32 dB with broadside radiation. Broadside radiation pattern is desired especially for implantable antennas, as it allows the antenna to generate strong signal which can be easily detected by external receiver. On the right, we have 2D radiation pattern. We can clearly see a broadside radiation pattern. In HFWorks, we have what we call far-field results table. This table summarizes some of the antenna important parameters such as directivity, gain, radiation efficiency, and total efficiency. Alright, so let's look at the effect of several parameters on the performance of the antenna. So first, let's start with the effect of dimension L. As we can see from the return loss on the right, increasing the length L leads to reduced resonant frequency. A longer arm length increases the current path on the patch and the effective size of the antenna, which results in lowering the resonant frequency. As we mentioned earlier, using substrate is important in implementable antennas as it prevents short circuit between the antenna and the body tissues. So in this study, we want to study the effect of 3 different substrate materials: Teflon, quartz, and Mycore. From the return loss plot on the right, we can see that increasing the permittivity of the substrate leads to reduced resonant frequency. So basically, higher permittivity of substrate makes the effective wavelength shorter and hence lower resonant frequency. So from this study, we can see that the quartz gives the best performance as compared with the other 2 materials. From the previous slide, we saw that quartz gives desired return loss as compared with Teflon and Mycore. So now let's look at the effect of the substrate thickness on the performance of the antenna. So for this, we have 3 different values for the thickness: 1 millimeter, 1.5, and 2 millimeter. So from the return loss plot, we can observe that increasing the thickness of the substrates leads to increased resonant frequency. So the reason for this, as the material thickness is increased, the respective effective permittivity decreases due to the insulation of the antenna from the higher permittivity tissue material. Hence, the resonant frequency increases. Now we'll have a live demo where we'll show you how to design and simulate such antennas using HFWorks. Welcome again in this live demo. HFWorks is fully embedded in SolidWorks. So basically, you don't need to import any geometry. Once you finish creating a geometry in SolidWorks, you can just go ahead and start your simulation inside HFWorks. So it's simply just a tab. In HFWorks, we have 4 types of studies. We have antennas, S-parameter, TDR, and resonance. But today we'll focus on antennas. So first, let's start with the antenna geometry. So this is the antenna. So this is the substrate. And now let me show the superstrate. Maybe I need to change its transparency. So we can see this is the superstrate and this is the substrate. Also, we have the body tissue. So this is the simplified body tissue. So the top one is the skin, the middle one is the fat, and the bottom one is the muscle. Also, we have the radiation boundary, which is the air. You can see it. Let me hide them since we don't need them for now. So in HFWorks, first we need to define the study properties. Under study properties, we can, for example, choose the type of solution, whether it's normal or high accuracy. Also, we have the frequency settings. For the frequency, we have different frequency sweep. We have fast sweep, discrete sweep, single point. Also, we can import your frequency points from a file. So for our antenna, the start frequency is 300 megahertz, the end frequency is 500 megahertz. We have 201 frequency points. In HFWorks, we have two meshing methods. We have adaptive and also we have the manual mesh. So for the adaptive mesh, which is automatic mesh, so basically the software try to find the appropriate mesh for your structure. In case if you are interested in some thermal studies, you can enable the thermal coupling. In HFWorks, we have our material library, which consists of a large number of materials with the predefined properties. So for instance, if we go to the biological materials, let's for instance choose blood. So now we can see the blood properties for different frequencies. Also, you can create new material library, or if you have your own material library, you can simply import it by clicking on Load Material Library. You can also edit the material properties by simply right-click and say Edit Material. You can edit the material property you want. After applying material, the next step is the setting the boundary conditions. We have different boundary conditions. We have port, we have lumped port, we have lumped element, PEC, PMC, PEC symmetry, and PMC symmetry. So those two boundaries conditions sometimes are used to simplify the structures and hence save some simulation time. So in our study, so we have this lumped port with an impedance of 50 ohms. Also we have the PEC, which is the radiating part of the antenna. Also we have the signal, and also we have the radiation boundary, which is the air. So to see that, we need to show the air. So now we can see the radiation boundary. Also we have the mesh control settings. If you right click, you say apply mesh control. So you can apply mesh control on bodies, faces, or edges. You can also specify the element size. If you want to see the mesh, you simply right click, you say for instance last adaptive mesh. So you can see the last adaptive mesh. Alright, so now let's look at some simulation results. In HFWorks we have what we call a results table. So a results table summarize the circuit parameters such as generalized ACE matrix, renormalized ACE matrix, impedance matrix, port results, VSWR, and other parameters. So for example, our antenna has an input impedance of 50 ohms. You can print results. You can also export results to different formats such as text file, CIT, SPC, or touchstone. So this is the 2D return loss of the 2D plots, which represents the return loss of the antenna. So to create this plot, you simply right click and the plot, you choose 2D plot, and you specify what study and then the corresponding parameter, which is S parameter, and then okay. So now we can see the S11. Also we have the results table, which summarize some of the antenna important parameters. You can again print and export results to different formats. So now let's look at the 3D radiation pattern. So now we can see the antenna has gain of -32 dB. Also we have the 2D radiation pattern, and this is a polar plot. So to create this, simply you right click, so you choose polar plot, it says polar 2D, and then you say, for example, for phi equal to 0, you said add, and then you hit OK. You can even change its color, so it's pretty handy. So now let's look at the electric field. So this is the electric field of the antenna. We have different plot formats: fringe, vector, streamline, point, 3D mesh. We can animate. Simply right click, set animate. Also, if you want to, we have the magnetic field. You can again right click and say animate. So to see the SIR value, we need to show the body tissues. So now we can see the SIR value. If you want to change, if you want to find SIR value for different input powers, you simply right click, you say edit definition, and you can choose the input power. Maybe let me change the view. All right. So also we have what we call parameterization or parametric study. So through this study, we want to see the effect of this length L. So if we right click, we say parameter. So this is the parameter, as you can see. If you want to display geometry for different scenarios, you simply right click, say display geometry. Let's say for scenario 2. So now we can see the change of the length L. Same thing for the last scenario, 6.5. Yeah. Also, if you want to, for example, create the return loss for different scenarios, you simply right click, and then let's say, in this case, it says all, and there you go. So for the effect of different substrate material, so for this we change Superstrate to Teflon, and for another study we change Substrate to Mycore. And now we have here the results for different substrate materials. So lastly, it's same thing for the substrate thickness. So we try to change the substrate thickness to different values through this. So edit definition. So we can see different substrate thickness values. So now we have return loss for different thickness values. Here comes the end of the live demo. So to sum up, designing implantable antennas presents several significant challenges, including miniaturization, biocompatibility, patient safety, and signal attenuation. However, With advancement in electromagnetic simulation software, designers can optimize antenna performance, evaluate safety in realistic human body models, and overcome many of these challenges. With that, I would like to thank you, and now the floor is open for questions.